Okay, let's get started. Last class, you see where we have stopped. We covered those who have not come the last class. Kindly look at that. We started with flip-flops and its applications with module 3. Here we described what do we mean by combinational network and sequential network. Combinational and sequential network both are two-valued networks. Whereas in first case, combinational network output is a function of only input. Whereas with reference to the sequential network, output is a function of present input and past history. This we are already aware of it. Combination network doesn't have memory. Sequential network has got memory. That's one main difference which we can see from combination and sequential network point of view. Later we discussed about synchronous and asynchronous sequential network. I just quickly review. I don't take much time in going through the previously already covered the topics. I'll just quickly review. These are two things, definitions you must be aware before we move on to the next one. Later we discussed about bistable, basic bistable element. In this we have shown how to build a latch using two NOT gates. And we explained, this there's a feedback connection between output of one is the input of other one, NOT gate. This through this cross-coupled kind of connection, we can establish a memory. Okay, if Q is 1 and Q bar is 0 means we are storing logic 1 in that particular in cross-coupled connection here. Basically, data is storing in the cross-coupled. That means output is output of one path is the input for the other one. In this cross-coupling, we are using this. We are storing the data within this cross-coupled connection. This is a very important step in the sequential circuits. Okay. Later, we transformed this circuit into the NOR gates later. And we have shown equivalent of that using basic gates as well. And symbolic representation, IEEE symbols also we have shown in the last class. And the truth table, we analyzed each row with the conditions, R0, S0. And we have shown that what will be the next state for this. It will be no change in the next state. Similarly, we analyzed all possible conditions of the truth table. And this is another equivalent latch we built with the help of NAND gates. This is S bar R bar latch. You will see this importance when we go to the gated SR latch. And even this latch we are discussed with various combinations like case 1 with S bar 0, R bar 0. And we again showed that the both the Q plus next state and the complement of next state is going to become 1, which is unavoidable kind of state which we are seeing for S bar 0 and R bar 0. And look at other possible conditions here. S bar 0, R bar 1, the next state is going to be 1 and 0. This is called set state. Case 2, which is case 3 is actually S bar equals 1, R bar equals 0, where we get next state as 0 and 1. This is called reset state. And here we have last case with both 1 and 1, where output will be in the present state itself. Next state will be equal to the present state, or no change will be in the states. And finally, we have showed the equivalent symbols here. Okay, this already we have discussed it. Later on, we focused on how to build a gated SR latch. So you can see here the NAND part which we discussed previously is the last second stage of this. And before that, what you can see is the gates. We have used two NAND gates here. These are called gate. This is called gated flip-flop. In order to have a control of the second stage, we use here two NAND gates here. Okay. And for the two NAND gates, and you can observe the input here. One input is S input, other input is going to be the enable input. Generally, this is the one which controls the entire gate. Okay, this kind of flip-flop is also called as a steering flip-flop, because using enable, we can control the entire flip-flop. But this kind of enable, which we don't see in the previous, either we built a latch from the NAND gates, or we have built a latch using the NOR gates. In both the cases, we could not see the control, but here, with the help of additional two NAND gates, we can have a good control over this latch. Basically, latch is a combinational circuit which doesn't have memory, but if you have some control over that, you can have very good memory, very good storage. And when the data has to be stored here, and when the data has to be appeared here, that can be easily controlled through the enable signal called as a C here. Later we are going to make this enable signal as a clock signal. And look at the truth table of this, uh, 0, 0, and when enable is equal to 1, it goes to the present state itself. There is no change in the states. Q plus indicates next state, and Q plus bar indicates again complement of next state. And if you observe here, the next state is again same as the present state itself. Q plus is equal to Q, and Q plus bar is equal to Q bar. That means there is no change in the state when 0, 0 combinations. Okay, for 0, 0. This has been discussed here in detail. You can see that how we get here Q plus as Q, Q plus bar as Q bar. That is discussed here with all with more details. You can see here we have taken S0, R0, C1. We are assumed as enable as 1 here. And see what is going to happen in the this gated SR latch we have shown here step by step. We have discussed this in the last class. I don't want to go with more details. If you have any questions related to this, each cases you can also ask me before we move to the today's class, master slave JK flip flop. That's what I want to focus on that in today's class. Any questions about this, the case number, case 1, or even remaining cases like case 2, 3, 4, and 5, where in 4, last case you can observe here we have taken here the things to be considered is enable is 0, and irrespective of the inputs like yes input, set input, and reset input, that's taken as a don't care, and Q is assumed as 0 and Q bar is taken as 1, and you can see here the next state will be equal to there's no change in the state, it will be equal to the present state, there's no change in the state. We have observed here two things here. Even for the first case, when you make S is equal to 0, C, R is equal to 0, and C is equal to 1, the next state will be no change. Similarly, when you make here last state, you can observe, even when you make, disable this enable signal, irrespective of this S and R, still the gated SR latch goes to the no change state. Those two things are common here, which you have to observe here. Okay, gated D latch. Once you have understood the SR latch, how to build the SR latch, you can also go for the gated D latch. The only difference here from the SR latch to gated SR latch to the D latch is we clubbed together because we want to avoid the forbidden state, or so that 1-1 combinations we have to avoid. So therefore we have here connected here a inverter. So S and R now become single input now. We call that as a D input now. This is called, the D flip flop or D latch. You can call gated D latch is also a D flip flop, of course. And you can see the truth table of this. Since a D takes a 0, when enable is equal to 1, the next state is going to be 0. That means it is called reset state. And Q plus bar becomes equal to 1. This is a reset state. And when D is equal to 1 and the C is equal to 1, the Q plus, the next state is going to be the 1 and 0. This is called set state. That means we avoided the forbidden state by connecting an inverter among S and R. We don't have two inputs for this kind of flip-flop. We only have one input that we called as a D input, mainly to avoid the unavoidable forbidden state here. This is one of the most widely used flip-flop. Even in industry also, if somebody asks you which is the most widely used flip-flop, that is nothing but the D flip-flop, because this avoids all kind of the problems, errors which we encounter in the flip-flops. This is basically used to store a 1-bit information in. Even you can build very big memory, but for the foundation to build a very big memory is nothing but the flip-flop, which is nothing but D flip-flop. So I always suggest you to learn how to build D flip-flop, how to design D flip-flop. And this flip-flop can be used even in counters and other sequential circuits. That's what about the D flip-flop. I don't want to go more detail because once you have understood the SR flip-flop, there is nothing, you will not pay much attention to the D flip-flop, because only thing is we just connect both S and R input with the help of an inverter, mainly to avoid forbidden state here. I look at last row of this D flip-flop where we have enable is made as 0. C is called enable here. Sometimes we call C as clock also, but here we take it as C as 0. And D can be anything here. D can be 1 or D can be 0. Still, they can see the next state is going to be a no change state. Okay, so Q plus becomes equal to Q, and Q plus bar equals to Q bar. There is no change in the state. And I also advise you to go through these definitions like propagation delay, pulse width, setup time, hold time when you come across the flip-flop design. This is most important when you involve in the flip-flop design. Any questions before we move on to the next master slave flip flop? This is as per your syllabus. Now we are moving towards master slave flip flop. Here we need to concentrate two types of master slave flip flop. One we will take up initially with master slave SR flip flop, and we'll show that some errors we encounter in master slave SR flip flop, and that error can be easily overcome with the help of master slave JK flip flop. Okay, even master slave JK flip flop also has got some error, but somehow this is better. Master slave JK is better than the master slave SR flip flop. Okay, now let me quit now the discussion of latch. Now no more latch, because already we connected a gated. We have designed a gated flip flop. Okay, so we have a control over the latch. So latch is basically a combination circuit, and here we have two types of flip flop which we need to discuss. But from syllabus point of view, we only discuss master slave. We don't discuss edge triggered. Edge triggered is very important from industry point of view. Again, instead of accepting data for the entire on pulse of a clock, we only accept the edges at the edges of the clock. So such kind of flip flops are called as edge triggered flip flops. Anyway, I'm not going to discuss more detail of that, but only a hint I will give you how to design edge triggered flip flop. But basically, if you understand master slave flip flop, designing the edge triggered flip flop will not become too difficult. Okay. Okay, let's see. Let me move on to the master slave flip flop and discuss more details of this. What do you mean by master slave flip flop? We have got two stages here, two SR flip flops here. One is called as master, and other one is called as a slave. And here, master is again the SR flip flop itself. That's called first section. And slave is again another SR flip flop, gated SR flip flop. That is going to be the second section. And here the technique here is for the one edge of the one level of the clock, master is enabled, and another level of the clock, slave is enabled, and both are not enabled simultaneously. When master is active, it's just like a classroom and a student kind of analogy. You can take it even for master slave flip flop. When master speaks, when teacher speaks, student keeps quiet, and when students speak, the master keeps quiet. I mean, the teacher keeps quiet. Okay, so this kind of concept has been used, analogy has been used even the design of master slave flip flop. And how do we keep quiet? That depends on the clock pulse. In one level of the clock pulse, whenever clock pulse is high, master is enabled, slave will be disabled. Okay, I will show you that with the help of step-by-step clock pulse. One tricky, difficult thing for students to understand master slave is we normally don't pay attention for the timing diagrams, because that's very important when you involve in master slave flip-flop design. You have to pay attention for the timing diagrams. You will understand more details when you look at the timing diagram. Instead of going to the working principle, timing diagram plays a very important role. But anyway, what I want to say here is, at one level of the clock pulse, on pulse, let us say, when clock pulse is high, in the electronic way, if you can say, when clock pulse is 5 volts, master will be enabled, slave will be disabled. As I told you already, at any instant of time, only one should be enabled, either master or slave. And even if you observe clock waveform here, I will show you the next one. There is a stage in which both master and the slave both will be disabled. That's actually not a good sign, but anyway, you will encounter that in this kind of flip flops. Look at this. This is the a logic diagram. I don't call this a circuit diagram. There's a lot of difference between the logic diagram and the circuit diagram. Probably in circuit related subject you see more detailed transistor based circuits. But here we write only the symbolic representations here. This is SR flip flop, and we can see this gated SR flip flop. It's not latch now. I'm calling them as flip flop. As you can see here, S and R are the set and reset input, and the Q and Q. This is complement here. We are shown as a bubble. Complement input here. This normal and complement input. And same with the same the flip flop we have again used once again. We are calling this as a slave. As I told you, this clock signal or enable signal is connected to an inverter for the slave, the flip flop. That means at any instant of time, master will be enabled, or slave will be. When this is enabled, the slave will be disabled, and when slave is enabled, master will be disabled. That's how these two blocks will talk to one another depending upon what kind of clock you apply. Okay, that's how the circuit works. And I tried my level best to discuss all possible cases as you compare with the textbook. Textbook doesn't discuss more detail by going through each and every cases. I thought let me give you more detail so that you understand. You go back and if you look at the textbook, you can understand better. So that's the reason I have covered in more detail with all possible cases. Before that, let me show the construction. I already discussed about constructions. If you have any questions related to any of the notations shown here, you can ask me. Any questions related to the notations used? I hope you are clear with this notations. Look at your subscripts here. QM is indicated here. It's an output of the master. QM bar. Subscript here QM bar. It's again complementary output of the master. Similarly, here we have a QS, slave output, normal output. QS bar, complementary output of the slave. Okay? And this NOT gate is very important because whenever the clock is 1, the master will be enabled, slave will be disabled. Okay? When clock is 0, this will be, master will be disabled, slave will be enabled. And when slave becomes 0, when master becomes enabled, it captures the input, it takes the input. Okay? And it doesn't pass that output to the slave because slave is, whenever the master is enabled, the slave will be disabled. It waits for one more, the falling edge, okay, the low level. So whenever master is enabled, it takes the input, whereas this will be disabled. And at some point of time, the slave has to be enabled and master has to be disabled. Okay, next immediately after when the clock goes 0. When the clock goes 0, what happens here? The outputs of this, okay, this has got some propagation delay. We don't pay much attention to the propagation delay. Every circuit will have its own propagation delay. Let's assume that already the master has captured the input SLR, whatever you apply, and it has been changed its state. And this change of state will not propagate will not be acquired by the slave flip-flop until this slave becomes enabled. Whenever the clock becomes 0 here, the slave becomes enabled, and the state, whatever produced by the master, QM and the QM bar, that will become equal to the R input, and S will become equal to the QM. Okay, so that input will be captured by the slave when slave becomes enabled, and after some propagation delay, the slave will change its state QS and QS bar. That's how the working principle of the master slave JK flip flop. And if you understood this, then understanding the next one becomes easier, which is master slave JK flip flop. There's some errors which we encounter in this master slave SR flip flop that can be easily overcome in the master slave JK flip flop. Any questions regarding this notations? I've tried my level best to explain all the notations. As you can see here, S is called set input, R is called reset input, C is the clock signal, and now we are using level based triggering. It's not edge based triggering. As I told you, flip flops can be classified into two types. One is level triggered, other one is edge triggered. Edge means only when the falling edge or rising edge, we are going to change, the flip flop is going to change its state. Such kind of flip flops are called as edge triggered flip flops. But in industry, we use edge triggered flip flop. We don't use even level triggered flip flop. But here we are discussing the level triggered flip flop. Level means as long as the clock is 1, flip flop will keep on changes its state. What's the drawback of level triggered? Why we are not using them in industry? Any idea? What may happen if I use level triggered instead of applying here? What I'm trying to say is, as long as clock is 1 here, this will change its state, right? My question to you is, only this, if I make this entire flip flop as edge triggered, only when the rising edge comes here, this will change its state. When this misses the rising edge, when the clock misses the rising edge, this inputs are not captured. Understand? I always compare this with the train analogy. If you remember, once again, compare always clock with the train, and let me make you to understand how exactly this edge trigger plays a very important role. Look at here, whenever the train comes here, let us say, when the rising edge comes, train coming and stopping at particular place, nothing but the rising edge is coming here. When rising edge comes, this you can interpret like a passenger. Okay, this must be well in advance. This must be ready. Okay, the train will not wait for the first rising edge when it comes here, and if you miss that, what will happen here? When the first rising edge comes, whatever data is it will take and change its state. Understood that concept here? Suppose if the first rising edge is missed, what will happen? Even though in between, lot of changes happens in the clock, this flip flop, if it is edge trigger, that inputs are ignored. Only this will wait for the next rising edge. When next rising edge comes here, at that point of time, whatever the S and R inputs were there, it will capture that and changes its state. Such kind of flip flops are called as edge triggered flip flop. But now you see, what we are discussing right now is level triggered flip flop. It's not edge triggered flip flop. As long as clock is 1, I'm not telling now edge now. I'm not looking at edge. I'm looking at what? 1. When clock is 1, the inputs S and R are captured and the corresponding changes will happen here, QM and QM bar. You're getting this now? Now, what's the drawback of using level trigger now? Problem here is no. Suppose if you make this clock as 1, and you still if you cap, because clock pulse, it will be 1 for some duration, right? Okay. As long as the clock is 1, some noise also can propagate here, right? Are you getting what I'm trying to say? Some noise or what do you mean by noise? An unwanted signal, a disturbance. Understand it? Such kind of signals may apply as an input here because these are very important. These are data inputs here. As long as clock remains 1 here, the S and R, it can be anything. It can be useful data. It can be not useful data also. It can be noise also. That's a problem in industry. Whenever we use the level trigger, a noise can propagate it. But R may be perfect. Sometimes some noise may come with the R. Yes, may be perfect. Or sometimes R also may be perfect. Yes, some noise may be interfered here. That will create a lot of unwanted signals in the entire memory. The flip flops. Okay, so to avoid such kind of circuits, we always encourage students to design a edge trigger flip flop rather than the level trigger flip flop. But our syllabus point of view, we have only the level trigger flip flop, but you must learn the edge trigger flip flop when you go for industry based flip flop design. Okay, these are the few definitions which you must be aware of it, what we are trying to discuss here. This is about clock. Clock is, there are 2 levels of clock. Entire clock is very important in sequential circuit design. Clock can go from low to high or high to low also. In the clock waveform, you will observe all these things. Don't make perfect, the sudden rising and sudden falling kind of waves in the clock, because that's practically you can't design such a kind of a clock. Have you observed anywhere the sudden rise in the signal? Let's give an example here. You might be designing A-stable multivibrator, right? Observe the output waveform of an A-stable multivibrator. It's always slowly it will rise and go to the high level. And even falling also it will not happen immediately. Slowly it will fall and it will take its own time to fall. Let me give an analogy for that. Suppose if you have a bike or two-wheeler or car, whatever, you may reach the constant speed after some time only, right? Assume that your initial speed is 0. And you go to all the way, suppose your stable speed is going to be 80 km. Will you reach 80 km immediately? You will take it in your own time, right? That's called a rise time here. Even in circuit also, the clock what we say here, this is actually our real clock, practical clock. Okay, clock will take its own time to go from low level to high level. This is called a rise time here. Okay, I'm not given here rise time because that's not important for us here. Okay, how to define rise time? The time taken by the clock to go from low level to the high level. That is called rise time. See, it will take its own time. And fall time is reverse, just opposite of the rise time. The time taken by the clock to come from high level to the low level. Okay. These are the parameters. When you design this in a tool, you are supposed to give all these parameters as an input when you design a clock. Blindly, we can't design a clock with sudden rise and sudden fall because practical circuits will not generate clock with sudden rising and sudden falling. In any textbook, if you observe clock of this sort, it's a practical clock. That means author have been given attention to the practical aspects. Okay, if some textbook focus right clock suddenly rising and suddenly falling, it's an ideal clock, not a practical clock. Okay, that those things you must understand here. And with reference to the clock, we have 2 levels. One is low to high, that is called as rising edge. Whenever clock goes from low to high, this is called rising edge. The same thing we have captured there. Also, it can be called by other names like leading edge and positive edge. All are same, in fact. Okay. And high to low level, this is high to low level. This is a high level to low level when the clock is falling. Okay, this is called high to low level value 1 to 0. This is called falling or trailing or negative edge. All are same. In fact, you can call with any names, whatever you feel comfortable. Okay. Any questions about this? All details related whatever described in the textbook are given in the form slide. Please go through that. And also here you can see that till T1 the slave is enabled, and from T1 to T, this is what I was telling to you. Here you can't say which one is enabled here. Look at here, after T1, slave becomes disabled. And look at here, the master is going to get enabled only after T2. My question to you is now, what will happen between the T1 and T2? Small duration, right? Okay, you can't say that the master enabled or slave enabled between the T1 and T2. Same thing will happen even between T3 and T4 also. Look at here, T3, what is going to happen? The master will get disabled here. As I already told you that whenever the clock is 1, master will get enabled. Whenever the clock is 0, the slave will get enabled. But my timing here is now at T3, master will get disabled. Immediately the slave will not get enabled because slave will be enabled only at where? T4 state. These timings are very important here. Even the clock may be falling here because it has not fallen completely 0. Since clock will take its own time to fall from high level to low level, let's assume that at T4 the slave will get enabled here. If you ask me what is the state of a master slave between T3 and T4, we can't say anything. In the same way, between T2 and T1, we can't say anything. So these timings are very important. Please pay attention to that. Okay. Any questions about this? So we have told that what happens when clock is equal to 0. Clock is equal to 0 means slave will be enabled here. And when clock is equal to 1 and after T2, the master will be enabled. This is how the timing works. Let us apply this to the master slave flip flop and try to understand the working principle of master slave SR flip flop. This is what the truth table of master slave SR flip flop. We understood logic diagram, how to construct it, and now we have described here a truth table of master slave SR flip flop. Look at here, we instead of showing here with the rising edge like this, or like the falling edge like this, a rising edge we are shown as a pulse here. These flip flops also it can be called as a pulse triggered flip flops because whenever the pulse is 1, master will be enabled. Whenever the pulse is 0, slave will be enabled. That's why we have shown here the clock signal as a pulse signal. You can see a pulse. Okay, we want both high level and low level because at high level, one part of the circuit is enabled, the rest remaining part of the circuit is disabled. Okay, whenever the clock is 0, the remaining part of the circuit will get enabled. That's why this flip flop is also called as a pulse trigger. And these are the inputs, as you can see here. If you look at last row, let us start from the last row. Whenever the pulse is 0, you have not applied anything to the clock. You made clock as 0. And irrespective of the inputs are not considered. It has ignored now. What will happen to the output state now? It remains in the Q1 Q bar. Q1 Q bar means no change state. It means whatever the flip flop before you switch on, and immediately if you make a clock as 0, in previous state where you have switched off, it will continue with the same state. It will not change. State will not change. That is called no change state. And if you go to the first row now, okay, when you make again clock as 1 and 0 0 input, the next state will be the no change state again here. And for 0 1, again you can see a 0 1, this is called reset state. For 1 0, clock is 1, 1 0, this is called set state. And you have to observe this fourth row because this is an undefined kind of state, a forbidden kind of state. Clock is 1, but both are 1 and 1. In this case, what will happen to the flip flop? Both will be going low or both will be going high. We have to see that. The output, two outputs, what we said already with reference to the SR flip flop, normal output and complementary output, both going to the 0, both going to the 1 is not acceptable. But whereas for this 1 1 S and R 1 1 input and clock is equal to 1, there are chances that the flip flop will, both of them will go to the either 1 or 0. This kind of a state is undefined state. We can't say that. It's against to the complementary rule. Therefore, this state is called as undefined or forbidden kind of state. And this is a symbolic representation of master slave SR flip flop, as you can see here. Okay, and it's called postponed indicator because after some time you will see the results. You will not see the results in the master slave flip flop immediately because there are two stages are there. One stage is cascaded to the another stage. Okay, therefore you will see the output after some time. That's why this indicator, the marks here, it's a reverse L-shaped mark. It's called as a postponed indicator. And this symbolic representation of pulse triggered master slave SR flip flop. Okay. Any questions about this? Please go through that. And I think I've given different category before discussing this waveform. I want you to look at this stage, each of these cases. I've tried my level best to explain all possible scenarios. Case 0 0. First, you can see here 0 0. What's going to happen? So the truth table in one single table we have mentioned, but if you go through each one every stage, you will understand better. Both are 0 0. Okay, there's inverter here. You can assume any state here, whatever you want here, because this, if I assume here as 0 and this as a 1, and same thing I have done here also. Assumption you can see as 0 and 1. Let us see what will happen to the next state. You must be aware of all the SR latch before you analyze these things. Okay, because if you don't know the truth table of this individual block, you cannot understand the truth table of the entire, both the stages. Okay, assume that you are already aware. So remember the truth table of individual gated SR flip-flop. Based on that, I can tell you that if S and R both are 0, let's assume that this is 1. What will happen here now? 0, 0, we know that it's a no change state, right? So the 0 will continue 0, 1 will continue as 1. Understand it? And then now when the class becomes a 0, this will be disabled and this NOT gate will become enabled. That means this output becomes 1. The slave becomes enabled now here. And for slave, this will be the input now 0 and 1. For 0 and 1, again this output of this also will be the 0 and 1 only. Clear to all of you? Okay? Any questions for 0, 0? This is what we summarized in the truth table. No change state is nothing but Q plus is called as a Q. Q plus bar is nothing but equal to Q. Q bar. Such a state is called no change state. Similarly, look at this 0 and 1. For that, it will be 0 and 1. It's called reset state. You have to analyze individually what is going to happen here again. For 0, 1, clock is 1. You can see here, even though I assume as 0 and 1, that remains as 0 and 1 only. You don't see any difference here, but in the next one you will see the difference. Okay, so 0, 1 that will be fed as input. Whenever the slave becomes enabled, this states will propagate and change the state as 0 and 1 only. Though it seems to be like no change state, but it's not no change state. Because you apply input as 0 and 1, this is called reset state. Look at the third case. Third case is S is equal to 1 and R is equal to 0. And assume that clock will change. Because I can't write anything here, clock as 1 or 0. For some time, clock will be 1. And first clock is 1 means the master will be enabled. And when clock is 0, master becomes disabled, slave becomes enabled. Okay, let's assume that clock is 1 now. When S is equal to 1 and R is equal to 0, look at what happens here now in this. Forget about this part here, second part of the circuit. So here I assumed initially the 0 and 1 as the output states before I apply the clock. And these are the inputs. When the clock is say 1 here now, this will changes to what? 0 becomes 1 and 1 becomes 0. Look at the truth table of this SR flip-flop. Okay? It changes to the 1 and 0. So the same 1 and 0 goes as input for the slave. After some time when the clock becomes a 0, the slave will be enabled because the inverter is there. The slave becomes enabled, the 1 and 0 will change to the 1 and 0. Even though present state I was assumed as 0 and 1, the next state will be the 1 and 0. This is called a set state. This is a no change state, reset state, set state. And look at now, next one is very important now. What happens when you assume it as 1 and 1? As observing here, both are going to the 1 here. Okay? This is called undefined kind of state. Both going to the 1, output going to 1 is not expected here. So therefore, this kind of states is called undefined kind of. How this happens? Let us see here. When both are 1 and 1, clock is 1. This, if I assume initially as 0 and 1, QM as 0 and QM bar as 1, the next state will change to what? This will change to 1 and this also will change to 1. Because we already understood the truth table of SR flip-flop. Whenever the 1 and 1 and clock is 1 means it will go to the undefined kind of state, right? So already it has reached, the first stage reached undefined state, that is the master part. And when the clock is now 0, slave becomes enabled, the same undefined state will propagate through the slave, and slave output also will be an undefined state. Okay, so both will be in undefined state when S is equal to 1, R is equal to 1. So this is a drawback of the SR flip-flop, master slave SR flip-flop. We don't expect this from the master slave SR flip-flop. Okay, so this kind of state must be avoided. And here in this case, in this case 4, you can't eliminate this undefined kind of state. The only way is you have to modify this circuit in some other way and come out with avoiding this kind of undefined state. What is that circuit modification? It's nothing but the JK flip-flop. Okay, that's the modification suggested for SR flip-flop. Okay, any questions about this? Last state is this. Okay, as we have already discussed, when clock is 0 and whenever the clock becomes 0, inputs are ignored here. As you can see here, though I have mentioned here X and X here, it can be anything. We don't know that. You can also assume X is equal to 0 or 1 or 1 and 0, whatever you assume, but the state remains same. If I assume the present state as 0 and 1, the next state also will be 0, 1. And even at the slave, whenever the clock is 0, the slave will be enabled. At that time, it produces no change state. Okay, so this everything has been summarized in the truth table. Please go through this truth table. Okay, if you understood this truth table, I think nothing else. You need not go for individual stages. But when you conduct this in laboratory, you are supposed to verify and show the examiner with all these possible cases here. Okay, any questions about this? Now we'll come back to the truth, this waveform now here. Okay, this is what I told you. Many students will feel difficult to understand this waveform. Anybody can tell me how do you understand this? Because after we explain the truth table, after understanding each and every cases, now can you interpret this waveform now? Yeah. How do we explain this now? The same way that we expand various cases, right? How did we start here? See, S and R, we don't have any control, right? That is an input, right? Look at here in the S and R, how it comes data from the user. See, sometimes he makes a 0, and at some point of time he made as 1. This is random in nature, right? Input. We can't have control over that. Where we can have control? No. Whether we want that data to be it has to go through the flip-flop or not, that you can decide by using a clock here. This is enabled, right? Understand here? You need not worry about S and R. S and R can be random in nature. We don't know. We are not interested in that. Understand? Whether train is interested in passenger, whether passenger comes in or not, train will come and stop at the place and it will keep on moving. Understand here? When you want to get inside the passenger, so that depends on the clock. Whenever the clock is 1, as I told you already, master will capture the input. What inputs it will capture, master? It will capture the S and R inputs, right? So as long as this is 1, you can see here, this is 1. So whatever the inputs you apply, that matters a lot. Only you should observe here, this timing instantly. Look at here now. S is 1, right? And R is 0 here. Now what should be the output now for this case? Clock is 1. Now truth table must be applied here now. S is 1, R is 0 this particular time, and the clock is 1. What we expected, the QM master output. It must be 1 only, right? So you can see here, after some propagation delay, this timing and this timing is not same. If you draw the line here, there is some gap given, right? What is that gap shows? It's a delay. Because master will produce, it will take its own time to produce the results at the QM and QM bar. This is what the delay, what you observe. Don't write exactly this, okay? Sometime you see that what happened here, the QM has become 1. All of you understood how this has become 1? Yes or no? Okay, because of this, S is 1, R is 0. Understand here? Only you should look at during this period. I told you we are not bothered about this S and R. Only when this is 1, at that time look at the S and R. Understand here? At this time you can see here, we start with 0. You can see here both are 0 here. And here it has been raised, and clock also is 1. That means your QM has to become what? 1. It has to become high after some propagation. It is high now. Now look at here, what happens when the clock becomes 0? Here also you must be curious now. Okay, now slave will be what? It gets enabled. Slave will be enabled here, master will be enabled here. Master, slave. Master, slave. That's how the enabling will happen here. Master captures input and changes the state of output. Understand it? When slave becomes enabled, slave takes the data from the master and it changes the final output. That's how the things work. It's a cascade. Now see what happens here. See, once you understood this, you will not see this because it's a complementary of what? The QM. QM bar is complementary of QM. Okay? Let us see here when the slave will be enabled here now. You can see here now. Now clock becomes 0 now. Understand? When clock is 0 now, see slave has been enabled. What will slave will do now? It will take the just master output, right? It is 1, you can see here. This is 1. This itself is our input for our slave, right? This is our R input and this is our what? S input now. So 1 and 0, what will happen to the slave output now? Clock is 0, only this period you should see for the slave. During this period, you can see here, this is R input is 1, QM is nothing but our R only, that goes to the slave. And you know that this S input is 0, 1 and 0, what will be the output of the slave now? It will be 1 and 0 only. So it is 1 here and 0 here. And again, you can observe there is a problem. This is the moment it falls here, low starts here. You won't see exactly same as this, right? There is some delay here. If you draw the line here, this will not fall exactly as rising here. Understood this? Okay. And further you can see here, again you can see the master has been enabled here. When the master enabled, see what happens here. And look at the data inputs now. Whenever master becomes enabled, you should see the S and R. Understand it? Whenever slave becomes enabled here, this period, you should look at the QM and QM bar. Because these are the inputs for the slave. And for the master, these are the inputs. Okay? Now look at here, what will happen when the again master becomes enabled? Again one right here, 0, 0, it continues what? 0, 0. No change state only. No change state will be continued. So here, for some time it is 0, 0. No change, that means 1 will be continued here. But look at here now, R becomes 0 now, both are 0, 0. Now what happens? Still your clock is enabled is 1 now here. Because of 0, it falls here. You can see it falls here and it continues now. Understood this? Any questions? Okay. So try to understand this each and every. You can draw the line, but here the author has not made any, timing wise, he has not shown the waveform. Randomly it has been drawn here. But I would suggest you to draw this waveform timing wise, and you understand better each and every timing instant what is going to happen. Understanding? Any questions about this timing waveform? This is important because this will summarize everything whatever we discussed, starting from the circuit, truth table, and 5 cases what we have discussed, and that is summarized in this timing diagram. Slowly you pay attention and look at each and every timing instant. As I told you, analyze step by step. Okay. The first thing is you also always look at the clock. When clock is 1, you must look at what? S and R and master output. Understand? When clock becomes 0, what you are supposed to look at? The master output and the slave output. Those 2 things you should look at. So if you are able to get these 2 things, I think you can understand this master slave. There is no difficulty in that. Okay, let me move to the next one, which is JK flip-flop. You already know why we are moving to the JK flip-flop. What is the problem with SR flip-flop? The only state is undefined state. Undefined state, because whenever you apply 1 and 1, what it will do? Both will be 1. That is not tolerable. That's a forbidden kind of state. That's what the SR flip-flop will do, master slave SR flip-flop. To overcome that problem, we have something called important flip-flop called JK flip-flop. Jack Kilby is a person with whom he has designed this complete flip-flop. Remember that when 1980s or 1970s, I believe it, these were the ideas, designs have been come out as a research papers. Today you don't see these things in IEEE or any portals, because they're all outdated. But at that time, long back, 1970s or 1980s, when these flip-flops were invented, at that time they were published as a research articles. Okay, at that time there was no computers, there was basically the typewriter, and normally whenever you want to publish a paper, people used to type it and write diagram in hand, and they used to publish in the journals. Okay, so those kind of literature you don't see in present scenario. You may see latest advanced kind of the designs, but not the old designs what you are seeing here. 1970s, this what you are seeing right now, the diagrams, the logic diagrams, they were published as a research papers. First, in the first instance, whenever the idea comes to the designer, they publish as a research articles. Later, that will be converted as a textbook. Understand? That's why if you are reading a textbook, you are probably the 10 to 15 year old things you are reading, not the latest things. How do you get the latest information about any technology or about any subject? Research papers. Understand? You should go through research papers. Probably the portal like IEEE, Springer, Elsevier, the top the publishers are there. Okay, and also look at that. More people are fascinated about ideas. That impact factor of the journal will go high. And today, if you see that impact factor of like medical journals, especially, it's very high. Okay, almost 45 to 50. The medical journals, especially. There's a lot of demand for that. Understand here. And if you look at another side, the journals related to the technical papers like electronic or electrical, it lies between the 2 to 10. You don't see much impact factor for this. Why it is impact factor is less? Again, utility depends, right? How many ideas will convert into the product? How many industries will use your ideas into the product? That depends. Okay. But in case of medical, there is a huge demand. But in case of technical, always impact factors lies between 2 to 10. A very good journal in electrical or electronic, it will be a 10 only. Even computer science for that matter. The impact factor will decide what's the quality of the journal. How many people are using that particular ideas, that depends on the impact factor. That's one of the important criteria. Okay, anyway, that's related to the old stuff. Again, this is master slave JK flip-flop. What is the difference between this circuit, this logic diagram, and the previous logic diagram what we have discussed? Yeah? Two AND gates are there, that's one thing you observe. Anything else? Yes, the feedback is coming from, say, look at here, this is a feedback which is coming from here. From Q bar, we take feedback and connect back to the SR flip-flop through the AND gate. You can see here, this is coming from where? It's a QS bar which comes here. And look at here for the another input for the second AND gate. It comes from the QS. We take output from here and we connect this back to this. See, simple ideas. Always simple ideas will lead to the breakthrough. Okay. In electronic, you do not do very big research. Always small ideas here and there, small stuff. It gives you big breakthrough in that particular domain. Understand it? But nobody has the thought before this invention, right? Look at this. People were using SR flip-flop in 1975 and 1980s. And this idea was, as I told, came as a research paper, and everybody started adapting this JK flip-flop. Even today, many will use JK flip-flop in small applications because they don't want to use a forbidden state. Here also we come across one problem called as a racing condition. I will be explaining to you later on. But anyway, the D flip-flop is one of the most widely used flip-flop. And this flip-flop will try to see that how this unavoidable, undefined state is avoided from this. Look at this. As I already told you that this is the connection. This comes from here and goes to this. And this connection from here, output goes back to the gate. Additional two AND gates were using it. That's the only difference between SR flip-flop and the JK flip-flop. You are adding, complexity by adding additional gates. Understand? So remember, this is one flip-flop and two AND gates. And imagine that you want to build, a 1 GB memory. Every bit, you are supposed to use two AND gates, right? And so don't look at memory from, a single bit point of view. A flip-flop point of view looking, is very difficult. It becomes very simple. For a flip-flop, these gates are going to be, for you, it seems to be that, you avoided error by using just two AND gates. But same thing when you go for very big memory, the circuit becomes complex. Understand it? These things are built as, used in, very big systems. We don't use just a flip-flop alone. Understand? Today you see wherever you go in electronic system, we will have a memory, right? Tell me the electronic system without any memory. Is there any system can be built without memory and without flip-flop? I don't think. So far I have not designed any such kind of systems without memory. Understand? Even, small blocks also we want a memory. The moment you capture input, you want a memory. The first part of your digital system design is memory. In fact, we are supposed to teach that, but anyway, the second part of the logic design, which is memory design. But this is even for combination also. To store data, we want memory. We may say that, see, combination, we can produce data and anybody can see it, but how do you reproduce it back? In my design, for every design like adder, subtractor, multiplier, I used enormous amount of memory. Understand it? That I can't tell you, orally, but when I show you some circuits, you will understand how exactly I use memory, even in simple adder design. Understand? My view is I'm looking logic design in different perspective. Whenever the computation part comes in the logic design, I use combinational circuit. And when computation is over, I store them in the memory. Are you getting it what I'm trying to say? Okay. Suppose if I ask you to develop some square root or some logarithmic kind of circuits, you will do some computation in that, right? After computation, you are supposed to store data. You computed data. Otherwise, what happens? You lose data. Understand it? Like you write notes, so whatever I say, you write notes, right? What is the purpose of writing notes? You lose information. You can't keep everything in the head. Understand? After some time you want to go back and see that, right? That's why we keep writing it. Same way, same concept is used in logic design also. Whenever combinational circuits, it may be the encoder, decoder, multiplexer, all the circuits doesn't have memory. When they do some calculations, when they change some data, output data, you must store them. Otherwise, you lose the data. Though we don't say in combination circuit in the first module 1 and module 2, we haven't said that combination circuits need memory. But in today's scenario, I will tell you, general electronic system design needs memory in each and every part of the system design. Anyway, so let's focus on this, how this works. We got the truth table. What difference you see from the truth table of this to the truth table of SR flip-flop? Look at here. The state has been avoided, right? Earlier this was undefined state. Now it has become useful state. What is that useful state? Q bar and Q. Look at here. Q plus next state becomes complement. Q bar. And next state complement becomes normal. That means toggle mode. This is called toggle mode. Whenever you have the 1 and 1 at J and K input, and the clock is 1 means the flip flop will go into the toggle mode. Toggle means previously if you assumed as 0, next state becomes 1. Previously if you assumed as 1, next state becomes 0. And it keeps on toggle. It doesn't remain in one particular state. It keeps on toggle. Toggle means it becomes 1, 0, 1, 0, 1, 0 like that. Here in this case, if you assume toggle means it will keep on changing. 0, 1, 0, 1, 0, 1, it will keep on changing. And if you observe that in the LED will start blinking always. Understand it? Such kind of mode is called the toggle mode. Okay? I hope you understood this. In detail, I have again different cases, just like I showed you for master slave SR flip-flop. I'll show you 4 different cases, but this is summary of all the possible cases. Totally, we have here 5 cases. 0, 0, no change state whenever clock is 1. 0, 1, 0, 1, this is called reset state, clock is 1. 1, 0, clock is 1. Output also it is going to 1 and 0, this is called set state. 1 and 1, already told you, it's called toggle mode. And for 0, whenever the clock is 0, ignoring the inputs, irrespective of the inputs, the Q plus becomes Q plus bar becomes Q bar. That means there's no change in the state. And these are the symbols for JK, master slave JK flip-flop. Okay. Now I don't take much time. You already know the truth table. Now just start analyzing this truth table. Anyway, I'm going to share the slides. Once this module is completed, I will share complete slides. You can go through that, each and every cases. Sometimes in textbook they will not describe everything. Textbook sometimes they go in a clumsy manner. They can't, author cannot explain. I cannot write the textbook from the student point of view because it's an international textbook first of all. And there are universities, big universities also use the textbook. And this book is also used even for master degree programs. That means author cannot write, make it very simple as like a guide. That's why always one of the textbook will be the standard one. Understand? If you are studying that in undergraduate program, you have to pay a little bit attention, read 2-3 times to understand the idea presented by the authors. Just if you glance 1 or 2 times, you cannot understand. Generally, I need about the 5 to 6 times to understand one particular topic. Understand? At different times to read, you get different idea, different kind of thoughts can be captured from the same topic. If you just read one time and if you ignore it, it will not work out like that. Understand? You read multiple times, like a story you must read. Understand better. Okay? Anyway, I don't want to teach you how to read. It's all the known things. I hope I don't want to go for more details. I'll leave it to you. These things, all 5 cases. Please go through this. And again, this is just like previous timing diagram, the way I've explained here. I'll just only tell you the toggle mode. Where is toggle mode here? Can anybody explain? Where you can see the toggle mode in this waveform? You see toggle mode? Where is? You can't tell in black once anyway. This is a toggle mode. Both are 1-1. Look at here. Both are 1-1. Clock is 1. What is happening here? 1, 0, 0. And this has propagated data. You can see 1, 0. Are you seeing this? This is called toggle mode here. This time you can understand whenever 0, 1 is there at the input, 0, 1 will be propagated to the output. Whenever there is a 1 and 0, clock is enabled, means the 1 and 0 will be propagated. Whenever this is 1, inputs will be captured. Whenever the clock is 0, the master output will be captured. Okay, that way you must understand this entire waveform. So in the next class I will pay much attention, and if anybody not understood this timing diagram, I can explain you once again here. Any questions about this? I'll stop at this point and continue with the next class.